Welcome to our video lecture on gas law, chemistry, kinetic molecular theory. Our objectives for today, we're going to define and describe kinetic molecular theory. We're going to review properties of gases. We're going to describe and apply methods of measuring gases. We're going to introduce the ideal gas constant. We're going to talk about some phase diagrams, including triple point and critical points. And we're going to wrap up with a little look at supercritical fluids. So first up, let's talk about this thing called kinetic energy. Remember that kinetic energy is the energy of motion. Kinetic molecular theory states that all matter is in constant motion, and gases are especially good at moving. Gases are in constant random motion in straight lines. So they'll kind of zip in a straight line and bump into something and then bounce and then zip into something, pretend like that's a straight line, and then bounce and then keep moving in straight lines, random motion. Just kind of bouncing off of lots of things. We make some assumptions about the movement of our gases. We know that the motion is very fast. Oxygen gas at 20 degrees Celsius, which is a chilly room, is moving at 1,700 kilometers per hour, smashing into your face right now at 1,700 kilometers per hour. That's crazy sauce. But they're very, 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 very small, and we're used to it, so it doesn't really bother us. Some more assumptions. We're going to assume that these gas particles are not attracted or repelled. In fact, they are attracted to each other sometimes. They are repelled by each other sometimes. But we're going to make our math a little bit simpler, we're going to pretend like those particles have no mass, have no forces of attraction or repulsion. We're also going to work on the assumption that all of the collisions when gas particles run into each other or into your face, we're going to work on the assumption that these collisions are elastic, which means that all of the energy of those two particles running into each other, all that energy is conserved, and then it's taken with the particles when they bounce and run away from each other. So elastic conditions, energy is transferred but not lost during those collisions. Let's review some properties of gases. We learned this back in middle school, so it should be quick and easy. Gases have no definite shape or volume. They're going to take the shape and volume of their containers for the most part. Sometimes, if the pressure is too small, the container might implode. If the gas pressure is too big, the container could explode. But most of the time, they're going to take the shape and volume of their containers. They're highly compressible. That means that we can take those gas molecules and squish them closer to each other. They have low density, and the reason is because they're spread out so far away from each other. A little bit of mass taking up a lot of space. They also move crazy, crazy fast. So our gases are here, shape of the container, volume of the container. That's different from liquids. Liquids are going to take the shape of their containers, but they're going to keep their own volume. Solids are going to keep their own shape and their own volume. Let's pause and practice those ideas. What state of matter, solid, liquid, gas maintains its own shape and volume, takes the shape and volume of its container, takes the shape of its container but maintains its own volume? Answer those questions in the Ed puzzle right now. So hopefully you decided that maintains its own shape and volume. That's a solid. Takes the shape and volume of its container. That, of course, is a gas. Takes the shape of its container but maintains its own volume. That's going to be a liquid. Let's talk about ways to measure gases. So first way we're going to talk about today is measuring molar mass. We use the periodic table to do these calculations. The molar mass of oxygen gas is going to be equal to 15.999. That is the mass of oxygen on the periodic table, but because oxygen is diatomic, it's an O2, we're going to multiply that by 2, and we're going to get a molar mass of 31.998 grams per mole is the molar mass of oxygen gas. In the Ed puzzle, go ahead and find the molar mass of hydrogen gas. Surely you found that hydrogen has a mass on the periodic table of 1.008, but it is also diatomic, and so we're going to multiply that by 2 and get 2.016 grams per mole is the molar mass of hydrogen gas. We can also use our molar mass to find moles of gases. So if I have 8.8 grams of hydrogen gas, how many moles is that equal to? We always start with our given, and 8.8 grams of hydrogen gas is our given. Since we want to convert that to moles, I'm going to take this gram here and put it on the bottom. So then my grams cancel out. Flip our grams into moles, put moles on the top. We just figured out that hydrogen gas has a molar mass of 2.016 grams per mole. 2.016 grams per 1 mole. Grams top and bottom is going to cancel out. We're going to use our calculator to do 8.8 times 1 divided by 2.016, and that's going to give us a grand total of 4.3650. Oh, so many digits. Let's do a sig fig check. I get to keep 1, 2 sig figs. So our final answer is going to be 1, 2 sig figs. That 6 is going to flip that 3 up to a 4. Final answer, 4.4 unit label moles of hydrogen gas. We can also measure the volume of gases. We like to measure volume in liters. Remember that the molar volume of an ideal gas at STP, standard temperature and pressure, is equal to 22.4 liters. So 22.4 liters per mole at STP. Standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere of pressure. So I want to figure out how many liters is 3 moles of hydrogen gas equal to. So we're just going to do our 3 moles. That's our given. I want to flip my moles into liters. I'm going to put moles on the bottom, put liters on the top. We know that there are 22.4 liters per mole, 22.4 liters per mole. Our moles, top and bottom, will cancel out. And with our handy-dandy calculator, 3 times 22.4 divided by 1 gives us 67.2. Unit label is liters. Let's do a sig fig check. I only get to keep 1. So that 7 is going to round that 6 up to a 7. Our final answer is 70 liters of hydrogen gas. Go ahead and do this one in the Ed puzzle now. Our given is 11.2 liters. We know that there are 22.4 liters per mole. Liters top and bottom is going to cancel out so that we're left with moles. We're going to do 11.2 times 1 divided by 22.4. That is going to give us 0.5 or 1/2 of a mole. But we need to keep 1, 2, 3 sig figs. So I'm going to throw a couple extra zeros here just so that we have the correct number of sig figs. Final answer should have been 0.500 moles. We can also measure the numbers of molecules in a sample. Remember that Avogadro's number tells us 6.02 times 10 to the 23rd molecules in 1 mole. So how many molecules if I've got 3 moles of hydrogen gas? Well, 3 moles of hydrogen gas, and we know that there are 6.02 times 10 to the 23rd molecules in 1 mole, because Avogadro's number tells us so. Moles top and bottom cancels out. And with our calculators, 3 times 6.02 times 10 to the 23rd, it gives us a grand total of 1.806 times 10 to the 24th molecules. Sig fig check, we only get to keep 1 sig fig, so our final answer is going to be that 8 rounds that 1 up to a 2. 2 times 10 to the 24th molecules of hydrogen gas. Let's talk about how we can measure the temperature of gases. We have been using Celsius in class all year long. Let's talk about this other super cool scale, Kelvin scale. So in degrees Celsius, 0 Celsius is equal to water freezing. So the freezing point of water is just about 0 degrees Celsius at sea level. But in Kelvin, 0 is literally 0. Absolutely no kinetic energy whatsoever. There are no negative kelvins. You cannot have a negative Kelvin because you can't have less than no energy at all. So 0 Kelvin is absolute 0, absolutely no energy whatsoever. Everything stops moving. How we convert between Kelvin and Celsius is this. We're going to take our degrees Celsius, add 273. That's going to give us our Kelvin. For example, if I have 100 degrees Celsius, that's the temperature at which water boils at sea level. And I want to add 273 to that. 373 Kelvin is equal to 100 degrees Celsius. Go ahead and do this one in the Ed puzzle on your own. You should have gotten 273 because 0 plus 273 is 273. What if I want to flip it around and I want to go from Kelvin back to Celsius? Well, if we have to add 273 to get from Celsius to Kelvin, to go from Kelvin back to Celsius, we're just going to subtract 273. So if I have 100 Kelvin, 100 minus 273 gives us a grand total of negative 173 degrees Celsius. Go ahead and do this one on your own. Remember that to go from Kelvin back to Celsius, we're going to subtract 273 instead of add it. Hopefully you found 27 degrees Celsius because 300 minus 273 equals 27. Another way that we can measure gases is by measuring its pressure. Pressure is literally how forcefully gas particles are running into their container or each other or whatever it is that they might be running into. So pressure is the force that push against the walls of the container or our faces or whatever it is that those gas particles are moving into. Atmospheric pressure is the pressure of the atmosphere, the air molecules in the atmosphere, that they exert on Earth due to collisions with objects like the ocean or mountains or us. So at sea level, we're going to call that 1 atmosphere of pressure. This graphic is super nice and it's showing us that most of the air molecules are kind of collected here toward the surface of the Earth. Gravity does a really good job of pulling those molecules down. The further away from the surface of the Earth we get, the fewer gas molecules there are. Which is why when you're on an airplane, we have to pressurize the airplane because the air pressure inside, the air pressure outside need to match so that the airplane doesn't explode. Up on Mount Everest, climbers might need to carry oxygen tanks with them because you can see from the graphic there just aren't as many air molecules, including oxygen gas molecules, that we need to breathe. So 1 atmosphere of pressure, 1 ATM, is one way that we can label our pressure. And that's literally Earth's atmosphere's pressure on the surface of the Earth at sea level. So 1 atmosphere of pressure, 1 ATM, is the pressure of the atmosphere here on Earth. We can also measure pressure in millimeters of mercury. So the barometer was invented quite a long time ago. This guy literally took like a bowl of mercury, super dangerous, but we didn't know it back then. So he took this bowl of mercury and inverted a vacuumed out glass tube, basically a graduated cylinder. And what would happen is when the air pressure was high, it would push down on the mercury in the bowl. And when we pushed on the mercury in the bowl, it would cause the mercury to go further up the tube. And then we could measure how many millimeters up the tube the mercury's symbol on the periodic table is Hg, how many millimeters up the tube the mercury would go. Hence millimeters of mercury of pressure. And of course, when the pressure was a little bit less, when the atmosphere was not pushing quite so much, that mercury could go back up in the bowl, which meant that it would sink down the tube a little bit. We would have a lower pressure because the mercury was not as far up the tube, fewer millimeters of mercury. The guy who invented this is called Torricelli. Torricelli was the guy who invented this barometer, and so sometimes we refer to millimeters of mercury as torr. They're the same things. 1 millimeter of mercury is equal to 1 torr because Torr invented barometers with millimeters of mercury. So 1 atmosphere of pressure, that pressure of Earth's atmosphere at sea level, is equal to just about 760 millimeters of mercury. Earth's atmosphere will push the mercury up the tube 760 millimeters tall. That'll be the same thing as 760 torr. So we can measure our pressure in atmospheres or in millimeters of mercury or in torr. But wait, there's more. The metric system unit of pressure is actually the Pascal, and we use PA as our unit label for pascals. We can use our metric prefixes like kilo. 1 kilopascal is equal to 1,000 pascals, and this will be a fairly commonly used unit of pressure for us. 1 atmosphere of pressure, again, the pressure of Earth's atmosphere at sea level is 101.3 kilopascals. So we can convert between atmospheres and kilopascals. But wait, we really like the number 100. So we decided we needed one more unit of pressure. Actually, we have a lot more. I'm just going to talk about one more. So 100 kilopascals is 1 bar of pressure. 101.3 kilopascals is 1 atmosphere of pressure. 1,000 pascals is 1 kilopascal. You don't actually have to memorize all of this. Some of it you do need to memorize, but the rest of it is listed on your handy-dandy constants and conversions list on your periodic table. 1 atmosphere is equal to 760 millimeters of mercury is equal to 101.3 kilopascals. Let's practice converting some of our pressure labels. So first up, 2.5 atmospheres to kilopascals. So we're going to start with that given 2.5 atmospheres of pressure. I want to get rid of atmospheres. I'm going to put it on the bottom. I want to flip it into kilopascals, put it on the top. We know that 1 atmosphere of pressure is equal to 101.3 kilopascals because that list on the periodic table tells us so. So now we're going to cancel out atmospheres top and bottom. Handy-dandy calculator says 2.5 times 101.3 equals 253.25 kilopascals. Kilopascals of pressure. We're going to keep 1, 2 sig figs, 1, 2. That 3 is going to leave that 5 of 5. Final answer, 250 kilopascals. How about 50 millimeters of mercury converted into just pascals, not kilo? So start with that given 50 millimeters of mercury. How many pascals in a millimeter of mercury? We don't know. What we do know is that 760 millimeters of mercury is equal to 101.3 kilopascals because both of those are equal to 1 atmosphere of pressure. So I can get rid of my millimeters of mercury and I have kilopascals, which is almost pascals. How do I get my kilopascals to be pascals? We're going to add one more chunk of railroad track. Kilopascals on the top, kilopascals on the bottom to cancel out pascals on the top because that's what I want to find. 1 kilopascal is equal to 1,000 pascals. So now I can cancel out kilopascals top and bottom with my handy-dandy calculator. 50 times 101.3 divided by 760 times 1,000 divided by 1 gives us 6,664.4736. So many digits. How many sig figs do we get to keep? Just 1. So that 6 is going to turn that 6 into a 7, and our final answer is 7,000 pascals. 50 millimeters of mercury is equal to 7,000 pascals. My friends, do this one on your own in the Ed puzzle. Hopefully you remembered that torr are the same things as millimeters of mercury because we don't have any conversion factors for torr, but we do have conversion factors for millimeters of mercury. So we're going to take those 800 millimeters of mercury, which are the same things as 800 torr. We're going to put millimeters of mercury on the bottom. We're going to put kilopascals on the top. We know that 760 millimeters of mercury is the same thing as 101.3 kilopascals. So now we can cancel out millimeters of mercury top and bottom. With our calculator, 800 times 101.3. Don't forget to divide by 760. And our final answer is going to be 106.63. Lots of digits. We're going to keep just 1 sig fig, 100 kilopascal. When we do calculations with pressure, sometimes we're going to need this ideal gas constant, which we label with R. What's kind of weird about the ideal gas constant, usually when we say constant, we mean it stays the same. Notice, and this is on your handy-dandy periodic table list of constants and conversions, we have 1, we have 2, we have 3 different R's. But the thing is, they're actually all equal to each other. They've just been converted from one pressure to another pressure to another pressure. So the values are all the same. They're just different conversions of each other. So we're going to learn this formula, PV equals nRT, where R is the ideal gas constant. If we're given a pressure of 1.3 atmospheres, a volume of 2.4 liters, and a temperature in degrees Celsius, and I want to find N, I'm going to need to plug in an R. What R do you think is the right R to use for this problem? Hopefully you're thinking probably the one that matches my pressure label, and you'd be right. So we're going to use this R value to solve this problem because I need the R value that has atmospheres in its label. Atmospheres in the label because I have atmospheres in the problem. What if I have this problem where now I have some pascals and my volume and my temperature, and I want to find N? What do you think I should do with my pascals? Which of my ideal gas constants should we use? I want you to answer this in Ed Puzzle. What should I do to my pascals? Which of the ideal gas constants should we use? We're going to have to convert those pascals to kilopascals by dividing by 1,000, and it's going to be 0.092 kilopascals. Once we have our kilopascals, we're going to choose this R value because it's the one with kilopascals. And just super little quick things, my friends, these milliliters, we're going to have to convert to liters to get that to match. And degrees Celsius is going to have to turn into Kelvin, add 273, so that those also match. So we've talked a lot about measuring gases. Now we're going to talk about some of the relationships amongst their properties. So this is known as a heating curve. It's the heating curve for water. What's kind of cool is that we can have ice, solid water that's super cold, -20 degrees Celsius. And we can warm it up until I have ice that is 0 degrees Celsius. At 0 Celsius, as I add heat, I'm adding heat over time. The heat is not going to be used to make the ice warmer. Instead, the heat is going to be used to convert the ice into liquid water. So this additional energy is going to be a change in potential energy instead of a change in kinetic temperature. Once we have all of our ice melted into water, then we can keep adding energy and we can make that water warmer, warmer, warmer until we get to 100 degrees Celsius. And at this point, we're going to add more heat over time, but the heat is not going to make the water warmer. Instead, it's going to convert that water into a gas, into water vapor or steam. We can also decrease the temperature of that water gas vapor. We can cause it to condense to become a liquid. Let's review really quickly this idea of compressibility. We're going to talk about this super quick, then we're going to call our day done, my friends. So compressible means that we can squish gases. Gases can be squished unlike solids and liquids. And what that looks like is here. So I have a low pressure system, gas molecules, lots of space to move around. But if I take this piston and push it down, 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 I compress those gas molecules. They're closer to each other. That means that they are running into each other and the wall of the container more frequently. And notice that the pressure goes up. So when we decrease the volume, when we compress it by increasing the pressure, decreasing the volume, crazy cool things happen. We're going to take that idea of compressibility and look at this thing called a phase diagram. So this is the phase diagram for water specifically. Different chemicals have different phase diagrams, right? And so what it shows us is that we can have some water vapor. So this is gaseous water at 1 atmosphere of pressure and 110 degrees Celsius. And it's going to be vapor. It's going to be a gas. And if I cool it off, but I keep my 1 atmosphere of pressure, but I cool it off, it's going to become a liquid. And then it can condense, well, it condenses into the liquid, and then it can freeze into solid ice, water, solid ice. So what's kind of cool is if I change the pressure, if I decrease the pressure and have very low pressure, we can actually go straight from the water vapor, skip the whole liquid, and go straight to a solid. And we call that, going from a gas straight to a solid, we call that deposition. Pretty cool. If we can get to this point right here, we call it the triple point, we label it C. We can get to this point right here, which for water is 0 degrees Celsius, and it's just about 0.006 atmospheres of pressure, my friends, we can have ice and liquid water and vapor, gaseous water at the same time. We can have a freezing, boiling beaker of water. Amazing! We call that the triple point, where we have gas and liquid and solid all at the same point. In the Ed puzzle, I want you to figure out what phase of matter will we be at 0.1 atmospheres and negative 10 degrees Celsius. How about 0.1 atmosphere and 40 degrees Celsius? How about 0.006 atmospheres and 0 degrees Celsius? 0.1 atmosphere is here, negative 10 Celsius is here. That's going to be a solid. 0.1 atmospheres are here, 40 degrees Celsius is here. That's going to be a liquid. How about 0.006 atmospheres and 0? That's our triple point, all three. We're going to have some solids and some liquids and some gases all at the same time. This is our last idea, the last slide of the day, my friends. You did it. So we talked about that triple point where we have solids and liquids and gases all at the same time. There's another point on our phase diagram called the critical point. So basically what happens at the critical point is stuff is so hot, it has so much energy, it is moving so crazy fast. It wants to be a gas, it wants to be a plasma. But I have made the pressure so very high. The pressure is so high. We're squishing things together, but they're hot and they're moving fast, but we're squeezing them together. It wants to be a gas, but it's stuck in a liquid solid kind of form, and we end up with this stuff that we call supercritical fluids. Supercritical fluids are crazy cool substances. This is the phase diagram for carbon dioxide. Supercritical carbon dioxide is used to decaffeinate coffee. We literally dissolve the caffeine out of the coffee beans using supercritical carbon dioxide. This is also how we do our dry cleaning. It's also how we make plastic. We can also use these supercritical fluids to kind of detox poisons, so we can steal electrons away from some toxins. Remember that oxidation, Leo says lose electrons is oxidation. So we can steal electrons away from toxins and make them not toxic anymore. So crazy cool. Before we go away from this slide, I do want us to look super quick at carbon dioxide really fast. So at at standard temperature and pressure, 0 degrees Celsius and 1 atmosphere of pressure, carbon dioxide is a gas. If I keep this 1 atmosphere of pressure, normal atmospheric pressure here on Earth, and I make carbon dioxide crazy cold, notice that I go from the gas to the solid. We totally skip liquid carbon dioxide. This again, going from the gas to the solid, is called deposition. So we can take that deposition of carbon dioxide, that solid CO2, my friends, this is dry ice, dry ice. And the reason that we call it dry ice is because it doesn't become a liquid, it goes straight to a gas. And the opposite of deposition, when we go from a solid to a gas, that is known as sublimation. Sublimation is the conversion of a solid straight to a gas, and it's what dry ice does. Dry ice, frozen carbon dioxide, totally skips the liquid stage at 1 atmosphere of pressure. And we did it! Good work! We defined and described kinetic molecular theory. Gases move really fast. We talked about some of those properties of gases. They take the shape and the volume of their containers. We talked about how we can measure gases. We can measure the molar mass. We can measure the volume. We can measure the pressure. So many cool things that we can do with our gases. We talked about those ideal gas constants. Really, there's only one. We just have a bunch of different labels, unit labels, conversions of that R value, that ideal gas constant. We looked at those phase diagrams and talked about triple point, where we can have a gas and a liquid and a solid all at the same time. We talked about critical points, where we get our supercritical fluids that dry clean our clothes and decaffeinate our coffee. Good work today.